All right. Hi, everybody. Just for the sake of time, we're going to start off with 0.4 first, and then if you need to do 0.2 and 0.3 for homework on Friday, I'll let you know. And so today we're going to talk about chi-square, and it's a form of statistical analysis. In order to answer the question, how does our observed data compare to the expected data? And this is going to help you figure out whether or not your data is statistically significant or not. So whether or not you're going to accept the null hypothesis or reject the null hypothesis. And so getting into our science practice, for chi-square analysis, you are going to need to calculate the chi-square value and use it to determine the p-value for a given data set. And we'll get into what a p-value is in a second. And using that, you're going to draw conclusions about your experiment and based on the comparison of the chi-square to the p-value. So you're going to compare your chi-square value to the p-value. And so, as we've learned earlier, remember we have an alternative hypothesis and we have a null hypothesis. And an alternative hypothesis is just going to state that there is going to be a relationship between the independent variable and the dependent variable. So this is a cause and effect relationship. And the null hypothesis is going to state that there's no relationship between the variables and that it's due to random chance. All right, again, so alternative, if you treat plant roots with the growth hormone, then it will cause them to grow faster. And then for null hypothesis, you're going to say that treating the plants with the hormone is going to cause no effect on how fast the roots grow. And so what chi-square test is, you're going to use this formula. And it's a statistical analysis tool that allows us to quantify and determine if our observed values. Our observed values are the data you collect, what you observe in front of you, the data that you have collected. What's the difference between that and the independent and dependent variables? All right, so you're trying to see if your data is statistically significant. And so if you say that your data is statistically significant, then it means that there is a high chance that your independent variable, right, the thing that you're manipulating, is what's causing there to be an effect. So it's causing there to be a change in the dependent variable. And so if your data table, and so then you're going to reject the null hypothesis. So if there is a statistical significance, then you are going to reject the null hypothesis because you are saying that there is an effect, there is a cause and effect relationship. And if the data is not statistically significant, then you're going to fail to reject. So you're basically going to accept the null hypothesis. So here you're saying that there's a very low chance that there is a relationship between the independent and dependent variables. So there's not going to be a cause and effect relationship. So when can you use the chi-square? There's like critical requirements here. You can only use the chi-square if you have a way to calculate the expected values in a normal situation. So here you can see that for genetics, you are able to expect a certain type of ratios using Mendel's laws. And so you can use the expected values to compare it to what you observed. So if you saw female red phenotypes and male red, and you're comparing it to male white, right? Phenotypes is the physical characteristics. Then you can compare that to your expected and see if there's a statistical significance or not. And so, yeah, you're going to compare the data you have collected, which is your observed data, what you have in front of you, to the expected data. And so calculating the chi-square value will allow you to, again, determine if there is a statistical significance, if the data is statistically different from one another. All right, so we're going to work it out using a coin flip example. And so when you think of coin flips, then you're expecting there to see a 50% chance of heads and a 50% chance of tails. And so basically what's going on here is that when you were to collect your own data, then if you were to get 27 times heads and 23 times tails, then you can compare those two values. So your observed data is the 23 tails and the 27 heads. And so what you would expect to see, right, based on statistics, is 25 and 25. And so your alternative hypothesis would be how you the scientific reason as to why this could be different. So what could cause it to be different? And so a cause could be if the coin is weighted, then you would see a difference between the observed and the expected, right? Then this wouldn't actually be your results. And your null hypothesis would mean that you are not seeing a statistical significance between your observed and expected. So the data you collected is consistent with what you expect to see in the real world. And so right now, can you say that there's a statistical significance, right? I mean, you do see that there's 23 tails instead of 25, and you do see that there's 27 heads instead of 25. But because you haven't done any statistics, you cannot say that there is a statistical significance. What you're going to want to do is use a chi-square test. Just because it's a little off doesn't mean that it's statistically significant, right? And so how do we solve that? So you want to, the first step you want to do is set up a table with columns. So you want to have an observed column, an expected column, an observed minus expected. Then you want to use that number and square it, and whatever number you get here, you're going to divide that by expected. So that's basically what this formula is showing us. And then at the end, you're going to get a sum, and that's going to be your chi-square value. So if we worked through this, then our observed values would be the amount of heads that you got. So you got 27 heads and you got 23 tails, right? And so our expected value would be to see 25 and 25 for each, right? Because that's what statistics tells us. And so when you subtract those numbers, for example, 27 minus 25 is 2. And then you want to square that number. So 2 squared is 4. And then you want to use that 4 and divide it by the expected, and you get 0.16. So you're going to do the math that way. Again, you square it to get positive numbers. So here you should always get a positive number. And then you're going to have your two numbers here. Again, your chi-square is the sum. So you're going to add 0.16 to 0.16, and you're going to get 0.32. From then on, you're going to figure out your degrees of freedom, which is represented by the equation n minus 1. N is the number of possible outcomes. So in this scenario, you have two outcomes. You have heads as one outcome and tails as another outcome. So you're going to do 2 minus 1, and your degrees of freedom would be 1. All right. So next, we're going to look at something called a critical value table. And because we have a degree of freedom of 1, then you're going to use your chart right here, and you're going to look for degrees of freedom 1 right here. And in biology, we usually use the 0.05 p-value. And so what we can see here is that our chi-square value is 0.32. And 0.32 is less than 3.8. So technically, our p-value is greater than 0.05. All right, so in this case, we are going to fail to reject the null hypothesis. And so the coin differences are due to random chance and not bias. Again, if your chi-square does not exceed, so if your chi-square value is less than the critical value, then you're going to fail to reject, or in this case, you're going to accept, right? That's another way to say it. When you fail to reject means you're accepting the null hypothesis. And so therefore, there is no statistical significance, right? It's just due to chance. If your number were to be bigger, if your chi-square number were to be bigger, then it would mean that you are going to reject the null hypothesis, meaning that there is a difference between the data you collected and, right, what you observed is the data you collected and what you expected. So in that case, you would say that there is a statistical significance between those. So there is something causing there to be a change, right? And so, again, in our example, you could read this over. It's basically just summarizing what I said. In our example, the degrees of freedom is 1, and the chi-square value that we got was 0.32, right? Again, let me go back to that. That was our chi-square value. And so comparing this to the chi-square value table, we see that our chi-square value does not exceed. It's less than 3.84 than our critical value, which means that our p-value is going to be greater. And then again, like I said, that means we are going to fail to reject or accept our null hypothesis, and it's due to random chance. So let's get into an example with genetics. All right. And so chi-square is perfect for genetics because we have Mendel's laws that can give us expected ratios that we, the expected ratios we will see in the real world. And so if we make a null hypothesis for this, then we would say that the differences between the observed and the expected numbers are due to random chance. There's nothing contributing to a change in our phenotype that we observe. All right, so then we're going to get into this problem. So if you were to walk around and you see peas, you see yellow peas and green peas, and you know that yellow peas are dominant over green. The peas you see are heterozygous, meaning that the alleles present are going to be both dominant and recessive. So again, your null hypothesis is going to be that there's going to be no statistical significance between what you observe. So you observe 4,400 yellow peas and 1,624 peas to what you, of the green ones, to what you expect. How do you calculate the expected? You do a Punnett square. Again, so this is what you observe. For Punnett square, you're going to do a cross between them. So because they're dominant, you see two heterozygous peas. Remember, you're going to see one dominant allele, one recessive from each parent. So this could be like the mother plant, this could be the father plant. And so the way you do this is go dominant allele, you work it this way. So one from the mom and then one from the dad, you fill it out. Again, one from the mom, one from the dad, fill it out. One from the mom, one from the dad, you fill it out. One from the mom, one from the dad, you fill it out. Because we're saying that yellow is dominant, anytime you see an uppercase capital A, then it's going to be a yellow plant. That's why I color coded it. And so when this one doesn't have a dominant allele, so this is going to be the only plant that's green. So this is not saying, this is giving you ratios. So you're going to have 75% chance that you're going to see a yellow flower, and then 25% chance that you're going to have 25% that you're going to have a green flower. You get this number by adding the amount of yellow and green, so you're adding them up, and you get 6,024. And so in order to get the total, you said that there's going to be 75% chance, so you're going to see, you're going to multiply 0.75 with this number. And so you expect to see 4,518 yellow plants, and then for green you expect to see 1,506. You're going to do the same thing. You're going to do the observed minus expected, then you're going to square it, and then you're going to divide that number by the expected all across. And then again, remember your chi-square is the sum of these two, so you're going to add that up and you get a value of 12.3. And remember, do you guys remember how to calculate degrees of freedom? It's n minus 1, n meaning the number of categories. You have either yellow or green. So you're going to do 2 minus 1, which equals a degree of freedom 1. And so our chi-square value is 12.3 with a degree of freedom 1. And so 12.3 is greater than, right, greater than our expected value. And because we said that if it's greater than, then your p-value is going to be less than expected. So therefore, you're going to reject your null hypothesis, and you're going to say that the differences between the observed and expected are statistically different. So what you observed in the real world when you were looking at your flowers is different than what Mendel's laws told us. So you are going to reject the null hypothesis, and you're going to say that what you observe is statistically significant. All right, and here's the recap. Please pause and make sure you understand this. If you don't, please ask me in class.